Welcome, everybody. My name is Willem Rosenbrand, and thank you for joining us for the fourth lunch lecture of the VvTP Symposium 2020Physion. I will be moderating today. We would love it if you turned on your camera. Do note that this lecture will be recorded and posted online, so if you don't feel comfortable with that, turn your camera off. During this week, we are looking at current innovations with vision on the future. Each lecturer will share his or her vision, and with every lecture this week, we'll look further into the future. We hope this will help you guide your own, to develop your own vision. Today, our speaker is Professor Niek Lopes Cardozo. Lopes Cardozo is a nuclear fusion professor at the TU Eindhoven. He's focused on the education and training of the ITER generation, so-called for the new and under construction nuclear fusion power plant in France. He is intrigued by the energy transition roadmap needed by 2050 and beyond. To reach the set climate goals in the short term, the current technologies will lead this battle, and only after 2050, better and greener innovative technologies will stand a chance. Hopefully this energy transition 2.0 is realized by 2070. This is his vision. Before welcoming Lopes Cardozo, a short practical note. At the end of the lecture, there will be time to ask your questions. Please ask these questions in the Zoom chat and also specify if you wish to ask these questions yourself or if we should ask it for you. Without any further ado, Niek Lopes Cardozo.
So thank you very much, and welcome all. It's great to see you all, and to have this opportunity to speak about a vision for the future. I'm going to share my screen, and if all is well, that should be. Okay. Can someone nod if they see my? Yeah. Okay. Great. Yeah. So let's talk about the energy transition. And I think this is really something for which a vision is needed. Maybe it's an aside that I hadn't planned, but of course you know the well-known quote from Helmut Kohl, who said, "If you have visions, you need to see a doctor." But others says, well, but for proper politics, visions are really necessary. And certainly, if you're speaking about things in the far future, 2050 and beyond, but that are of such overruling importance that they should govern our behavior today. I don't think you can handle that without a vision. But okay, where's the vision? Well, let's start with the planet. I assume we can agree that this is a vision. But if we zoom in a little bit, just Google Maps, nothing special. You see, this is Europe, and if we get a bit closer, this is Europe closer by, and now we are in the Netherlands, and now you're assuming that we're zooming in on Delft, but we aren't, yeah, because this is the future, right? So Delft is underwater. But there's a polder here. And this is an interesting part, because what's going to happen there? Well, let's see. We turn the view a little bit. And what shall we have there? How about this? Now, what is that? It's a power plant. And it's a power plant that doesn't produce CO2, and it produces electricity, and it's clean and safe and so. It looks like any other power plant, except that there's something here. Maybe I can indicate that here. This is the heart of the power plant, where the actual heat is produced that is then turned into electricity. So what's that? Let's have a closer look. Okay, this is somewhat confusing, but yeah. So that thing there is a nuclear fusion reactor. In fact, it's something we call a tokamak, but that doesn't matter. It's a toroidal chamber with magnetic coils around it. And in there, we can heat a fuel, hydrogen isotopes, to hundreds of millions of degrees. And in those conditions, we can produce energy. Let's get a somewhat closer look. Is it happening? Yeah, it's happening. So this is roughly what these machines look like. And we're building one. And the trouble is, it's incredibly difficult. These machines are called the most complex devices ever built by mankind. And we're not even sure we can do it. And the trouble, of course, comes forth from the fact that this fuel or this process only wants to burn at 100 million degrees or so. So you have to keep it hot, you have to keep it from the walls, you have to support it with magnetic fields. And then if you succeed in all of those things, there'll be an awful lot of heat that goes to the walls, and they shouldn't melt, and there are neutrons, so everything becomes radioactive. Basically, all the trouble you can find in any book is combined in this technology. But we are building one, and this is the present status. So this is called ITER. ITER is going to be inside that building just to show that it's big and that it's real, it's being built. But I stop here about nuclear fusion. Let's just say we're building a machine, and that machine should, for the first time, produce a plasma at those temperatures that is producing so much power that it's keeping itself hot. It still needs a little bit of control power, but it is mainly heating itself. And that is a completely new situation that we've never had before, and we need to build this enormously big machine for that. Now, so this is called ITER. Now I'm going to show you a slide that I made more than 20 years ago. And it depicts the roadmap for nuclear fusion. It starts with the Joint European Torus, which is an experiment that was ready in 1983 and has been running ever since. So it's still the largest experiment in the world in this field. It's a scientific experiment. It doesn't produce energy. It was never meant to produce energy. So now we're building ITER. ITER should do 10-fold power multiplication, which is a lot better than JET, but it's still no net energy production. So then we should have all the technology and physics worked out to the point that we can build a demonstration power plant. So that should actually produce electricity, but it's a demonstration. So not 24/7 and certainly not every day of the year. So don't expect to be rich from the electricity we sell with demo, but it's the starting point for development. So the present roadmaps as we know them in the research end with demo. So MO for your engineers, right? So would be TRL 7 or 8 or so. But what then? Well, then we should have the first commercial plant or plants. But yeah, there's 1 or 2 or 3 is not nearly enough, of course. So how many do you need? Well, you really need thousands in the end. To make an impact in the world, if every plant is like a gigawatt, and the world needs by that time about a gigawatt, and the world needs about 40 terawatts, you need 4,000 to do 10% of the world energy need. So the big question is, if we assume that we can do this one, how long will it take to go from there to there? And so for about 10 years, I used to give a talk with this slide and say, yeah, it's really not easy to go from 1 to 1,000. But I never worked out how long that would take. So then I asked the question, what is the quickest path to go from 1 to 1,000? And that made me come to the following considerations. Because then I realized this is not a question that's only relevant for fusion, it's relevant for every new technology, and in particular for new energy technologies. Because if you can answer that question, that puts like a limit on how fast the energy transition can happen. There are all sorts of factors, forces at play that make the energy transition happen more slowly than we should like. But but there's probably also a limit to how fast it could. So how fast can we make the energy transition happen at the fastest? Yeah, it's a question. So the answer is in this picture. And this is where I should ask you a question. It's with the interactive part. Maybe you can start typing your responses in the chat, and Willem can summarize them. So my first question to you is, the left picture is toothbrushes. Suppose you decided suddenly that you wanted to provide every toothbrush owner in the world with a new toothbrush. How long would you take? How long would it take to get that done? Are there any suggestions there? I'm looking at Willem at them.
We'll see. 2 years, I see, from Tim Kaas.
2 years, okay. Anyone longer than that?
1 year.
1 year shorter? Anything
1
shorter
year?
than that?
Another 1 year. 2 months.
Okay.
4
2
years.
months.
A couple of days. A wide range.
Good. Oh, good. Okay. Well, this is okay for the minute. So now we turn to the right-hand side picture, which is a house, for those of you who hadn't figured that out yet. And the question is, if we wanted to provide every house owner in the world with a new house, how long would that take?
I see 20 years, 30 years, decades.
Decades,
50 years,
okay.
50 years.
So for toothbrushes, it's months or maybe a year, and for house, it's decades. Yeah, and why is that? Now we can put that into language and say the average lifetime of a toothbrush is maybe a couple of months. You're supposed to take a new one every 3 months or so. So there's an industry that produces toothbrushes, and that production capacity is tuned to this replacement rate. So yes, in 3 months you can give everyone a new toothbrush. But if you wanted to do it much faster, you would have to suddenly increase the industry, which for toothbrushes is still something you could contemplate if the need was really high. For houses, those have a lifetime of 30 or 40 years or so. So if you wanted to give everybody a new house in a year, you would have to multiply the existing workforce and industry by a factor of 40, which you cannot do overnight. So there simply is not the capacity. Now, okay, so far it's completely straightforward, of course, but that means that the fastest way to build up a new toothbrush population, fastest is always a straight line, go from A to B is a straight line. And this is the fastest path. And so you start building up at day 0, and at day 100, approximately, for toothbrushes. The toothbrush of day 1 needs to be replaced. And your capacity remains constant, and this is the curve you get. Super. Now, what should this look like for houses? Well, it looks similar, except the time it takes. So you see that for toothbrushes, that's exactly the lifetime. So for houses, it's the same lifetime. So there it would be 30 or 40 years. Yeah. So there's a law here that says that if you want to build up a new population of a product, the fastest way of doing that is a linear growth, but that takes as long as the replacement time of the product, unless you're willing to build up an industrial capacity that's much larger than you will need in the end. And if you're talking about energy, jumping ahead a little bit, energy is the largest single market in the world with a turnover of 10,000 billion per year or so. It's bigger than food and pharma put together, which are the numbers 2 and 3. So if you build too much industrial capacity, you're talking about big money. Good. Now, let us just fill this in a little bit more. We used to have incandescent lamps, of the type shown here. And now we have switched to LED lamps. And LED lamps have a life of 20 years or so. So they could not be introduced much faster than in about 20 years. Otherwise, you would build an enormous capacity for building LED lamps, LED lamps, and then suddenly everybody has them and nobody wants another one anymore. So then the industry can go sleep for 20 years. But the phasing out the incandescent lamps, that of course could have happened with the lifetime of the incandescent lamp, like this. And that would have been a huge problem, because then there would have been a long time we all sit in the dark. So in retrospect, you may realize that somehow these incandescent lamps have been phased out really slowly. So first the 150 watts, and then the 100 watts, and then the 70 watts. It's not because we couldn't have phased them out much more quickly. It's because we couldn't build so many of the new ones. So you see these simple laws, so to speak, have a big impact on this kind of transition. Okay, back to toothbrushes. So for toothbrushes, this would be the curve. But then you say, yeah, hang on, but this presumes that you had an industry sitting ready here to start that line, but you didn't have that industry. So first you have to build that industry. Okay, so now it looks like this. So there's a soft start, and the soft start will also mean that there's a soft rollover at the end. Good, so far so good. This is toothbrushes. Now this is for houses. And now suddenly the days have become years, and the toothbrushes have become houses, but the curve is the same. So is this a universal curve, or isn't it? Now we make a jump to energy. And this is from a paper by Gert-Jan Kramer and Martin Haig in Nature in December 2009. And they simply looked at the historical, that is to say, the history at that time was until here. So this is all future. But this is historical data. And they said, hey, this is interesting. If you plot that on a log scale, all of them seem to go more or less exponential for some time, and then at some point they roll over. Yeah. So, and they phrased some laws, and they said, well, the exponential rate can be fast, doubling every 2 or 3 years, which is really fast. Yeah, but if you have to cover 4 orders of magnitude or so, that still takes 30 years. But then you get this rollover, and only then do you get to the linear development, which I've just described with the houses and the toothbrushes. And then unfortunately, as you realize, the hardware we built in the energy field is house-like and not toothbrush-like. And therefore the linear phase takes, well, typically a lifetime, so 30 years or so. Well, those are observations and simple considerations, and of course this can be put into equations. So if you know where you want to end up, so this is the end level, which you don't know, of course, because it's in the future, but sometimes you can guess. But just for the sake of explaining the model aspect, if you know where you want to go, so then the quickest way to get there would be a straight line. Okay. And as we have seen, the slope of that line is industrial capacity. Yeah, it's just how many of those units, whatever they are, you can build per year. And as we also said, but the largest industrial capacity you ever need is that which you need in the end phase to take care of the replacement. So that limits the slope of the linear deployment phase. Yeah, and that means that by the end of that deployment, the first installed units start to be replaced. Okay, all fine. But we needed to develop that industrial capacity before you can start. So that would typically go, I mean, you build an industry, you put a factory, if you think it's doing well, you build 2, and then you build 4, and this is how it goes, also supported by the historical data. So there's an exponential foot, and now we are scientists, so we say, okay, there's a time constant associated with the linear growth, which I call tau linear, which is equivalent, or at least close to, the lifetime of the product. And there's an exponential growth time, doubling time, which we saw for energy systems was 2 or 3 years or so. And if you then match at this transition the slopes, because the slope is industrial capacity, so that it has to be continuous, and also preferably in the derivative, then you can work out where the transition occurs, and that is at the ratio of the 2 time constants times the saturation. Well, if you apply this to energy systems, you realize that they typically have a long life, say 30 years, and the exponential time was 2 or 3 years. It's the 1/e time here. So the transition happens at 10% of the end value. So you cannot grow exponentially until you're there. You grow exponentially until you're at a factor of 10 from your end goal, and then you start to grow linearly. How different is this for smartphones, which have a life of 2 years, lifetime of 2 years? So then you grow exponentially, well, basically until you hit your head to the ceiling. You never have to worry about where you want to go, because the linear phase is so short compared to the exponential phase. So there's an essential difference. So if people tell you solar panels are going to conquer the world just like smartphones did, that's not true. It's simply not the same sort of proposition. Just to point this out, so on the left-hand side, it's here. This is the linear scale. This is a log scale. This is the plot in linear, on the linear scale. This is on the log scale. And what we'll see is that here, the exponential growth, if you plot this on an exponential plot, on a log plot, you see mainly the exponential growth, and then there's a little bit of that you see of the linear growth. But of course, in the real world, we are interested in the linear growth. The exponential growth is only there to learn how to do it, to build up industrial capacity. Yeah. So, exponential growth being exponential means that the last, well, doubling time, you put as much products in the world as in the entire history before that. And that kind of stays even because we know that the exponential phase ends at this fraction of the end level, that the energy production is by definition irrelevant. It's really about building up capacity and not about producing energy. And especially not if you're building systems that have to earn back their energy or start paying back over the course of 30 or 40 years. So the energy production isn't even happening during the exponential growth. This is something that is, well, okay, you're going to hate me for this, I'm pretty sure, but now I'm going to tell you something that unfortunately is a mathematical truth. So if the doubling time is shorter than the energy payback time, so take a solar panel, they're doubling really fast, which is great, with say 2.5 years doubling time. And the energy payback time for a solar panel is a couple of years. It used to be longer, it gets better every time, but it's certainly not much shorter than the doubling time. Then the net energy production of that entire process is negative. during the entire exponential growth. Yeah. So the fact that we are producing so many solar panels is increasing, not decreasing, the CO2 output in the world. And likewise, if the doubling time is shorter than the economic payback time, the net financial gain is negative and not positive. Yeah. And just to reassure you, these are mathematical facts. They're not criticisms. I'll explain that later. And anyone who runs a business, of course, knows that you have to invest before you start to earn money. And in this case, also to earn energy. So there's nothing more to it than that. But so every panel and every solar panel will produce much more energy during its lifetime than it costs to build it. So there's nothing wrong with that. But as long as you're building up that capacity so fast, you'll be spending more energy on producing panels than you get out of them. Yeah. So just to realize that as long as these things are growing exponentially, you're doing an investment in a future energy source. It's a good thing. We need to do it. There's no other way. There's no magic way of suddenly having another energy park. But you have to realize that this transition costs energy. So can we say how much that investment is? Well, yes, because we know the capital investment. So during exponential growth, there's very little payback economically. So it's really about investment and the capital investment in the end. So by the time you get closer to the end of the exponential growth, is typically about $3 to $6 per watt of installed effective power. So if for a solar panel, it's 50 cents, but then you still have the capacity factor. Yeah, and this is, so it's from nuclear to, and of course it has to be somewhat in a similar range for all those technologies, because in the end they're also competitors. So, and it's easy to fold that with the exponential growth, and then you get a number, and it says that, so by the time you get to the transition to linear, you're spending hundreds of billions of euros per year on the deployment of that new technology. And this is, you can check that if you go to the turnover in wind and solar, it's a few hundred billion per year. And if you integrate that over all those years per technology, but that's mainly the end, it's about 1,000 or maybe a bit more billion per technology to get to your transition. So to get to the point where you actually start to produce energy. It's not wrong, it's just a lot of money. Now we go back to that plot by Kramer and Haig. I redid it actually. This is more modern data, which is from the IEA and the global cumulative, the global wind energy consortium. Okay, I have to look up exactly what the name means, and the IAEA for fission. This is historical data, except for a small bit of extrapolation that is in those databases for the coming years. It's basically because you already know what they're building, so that will be solved hopefully. And well, of course, I fitted that model. Now, I don't want to put too much trust in this model as a prediction, but unfortunately, you see that there's already a bit of turnover. If you wanted to go high, if you wanted to end up like here, it would have been much better if wind and solar were still going straight in the log plot, but they're already showing a bit of rollover. Let's just hope that they can go back to going at full exponential growth rate. Because this ends up, I mean, if you take this seriously, I mean, it's the future, so a lot can happen, but then it ends too low, and that's not a good sign. Um, if you look at new technologies, yeah, you just take this figure and they say, okay, where's your technology? Where is it today? And how much power does it produce? And I'll tell you when it's so. Yeah. If you say, I have a technology and it sits in the lab, it makes a megawatt. Okay, well, it's not even on the chart here, so it's somewhere down here. And then you can follow it. You say, okay, how fast do you think you can go? And you know that you have to go linear in this plot, so exponential, until somewhere here, and then, yeah, there'll be a roll-off, and then you have to add a lifetime before you really start to produce energy. It's very hard to beat that. So where are we with fusion? I'd say at the best, we could have one demo reactor, one commercial, one demo, or a few demos somewhere here, and maybe they produce a gigawatt of electricity. And if we were to manage a 3-year doubling, of course there should be a rollover somewhere, but that still puts us at the end, at the turn of the century, at the best. And I'm not even sure that for reasons that I'll not explain now, that 3 years is an achievable goal for a difficult technology like that. So this would put fusion well into the next century. Are there other technologies we should look at? It's interesting to see what storage does. So electrolysis, which would turn electricity or electrons into molecules, if you want. Of course, storage would be energy, not power, but then if you know that you have to store for half a year, it still is a power. And it's behind, so the world has about 10 gigawatts worth of electrolysis ready. That's the most developed technology as far as I know. And it's about an order of magnitude too low. But okay, you see how it could pick up and sort of be there maybe when it's needed. But all other technologies that are presently in the lab, the stuff you read about in scientific papers and in the newspaper in the research pages, they're here, down here, you know. So I don't see how they are going to help us with the Paris goals, which live here. So these are the global CO2 emissions. We live at the dotted line. So this line is business as usual. What we need to achieve is something like this. And yeah, so we definitely should bend down this curve by using less than is predicted, okay? But still, to fill this gap, we need linear growth. We don't need this little exponential foot, which doesn't help us anything. It's just helping us to develop the industry. But what we really need is the linear growth. And we know how long that takes, a lifetime of the devices we build. So how are we going to save the world? And my statement for today is, well, until 2050, it's really down to the technologies we already know. And all the smart ideas we have, they're for later. Because the energy transition will not be finished in 2050. It's not like you look around and say, yes, we did it. Let's stop innovation. This is perfect. We'll always be looking for better. And if we are looking for better, we should do the research now. So I'm not saying we should stop researching, doing fundamental research in energy. On the contrary, but saving the world will have to do with the technologies we already know. As I saw, if you just follow the normal sort of economic laws, it's pretty hard to reach 2050. You really have to force the system to get there. And finally, if you take the logic of this little model, you'd say, so if you really want to go like the smartphone, you should have a product that doesn't live too long. Unfortunately, we think of sustainable energy like we build sustainable systems. But if you want to go fast, you should build disposable systems. And you can picture that if you had paint that you put on the walls of your house, and the paint is the actual solar collector. So now your business model is not, your business model is that you sell this cheap paint, but you sell people every 2 years a new can of paint. And nobody has to be worried that they're investing too early, because you have to replace anyway after 2 years. So maybe that is the final message. Go for toothbrush-like and not house-like if you do inventions in new energy. Thank you for your attention.
Thank you, Professor. It's very interesting lecture. So we're going to hold a small discussion. I already see a few questions incoming, but I have maybe a short question. How has your vision changed on the energy transition since you started your research? If you noticed that more pessimistic in it's not going to work or in time to reach goals, or like this, like what your lecture was about, that it's very difficult to reach climate goals.
Yeah, so when I started to put numbers to the question, how fast can you go? And I did the simple realization that if you have something that, even if you have something that makes, say a megawatt in the lab, a new technology, a megawatt is quite a lot in the lab, right? To bring it to 100 gigawatt, which would be even lower than the typical transition in the model, is 5 orders of magnitude. So 10 to this 100,000, so that would be 2 to the power 10 is 1,000, and then you have to another 7. So you have 17 doublings. And even if you do that every 2 years, which would be super, super fast, much faster than anyone has done, that is 35, 40 years.
Quite long.
And that's only the exponential growth, right? So then you're still not producing anything. You're just building up your industrial capacity. So there's, so is that pessimistic? Or I don't know. It's just a realization that you have that this is a system that's very difficult to force because it's so big. Because and that also means that, as I said, the turnover is very big. So the investments are also very big.
Yeah.
So maybe there's another lesson there that if you ask investors to invest an awful lot of money, then the risks should be small. So by the time you're deploying at a scale that is worthwhile, the risks should really be taken out of the system, because otherwise nobody's going to put those hundreds of billions.
Yeah, no one would invest. Yeah. I see your question from Paul. Paul, do you want to ask the question yourself? You can unmute yourself if you want to. Paul Adriaans.
Looking would be nice, yes.
Oh, go ahead. Okay. He has a question. What about building a tremendous overcapacity? So trying to beat the linear growth, I think, like continuously exponential. I think that's his question. Why not just try to improve, keep on building more and more and more?
Yeah, so that's an excellent question. So you could go on with the exponential growth. So first of all, if you could speed up the exponential growth, that would also help, of course. And you could continue longer than you need. So then you have too much capacity, but okay, there's also an economic lifetime on the capacity that you have built. So maybe that's not so bad. Depends a bit on what exactly you're building. So maybe if the lifetime of the product is 30 or 40 years, but of your factories, maybe it's only 20 years. So then it becomes 20 years. So you can overshoot a bit. Yes, you can speed that up, but not by a factor of 10 or so.
No.
I mean, that would be hugely expensive. It's of course it's been compared, for instance, to the Man on the Moon project. But the Man on the Moon project asked for 0.4 or so of the national domestic product for a couple of years. And this would be asking for several percents already, if you do it smoothly, of the gross domestic product for 50 years. So it is really of a different order.
Yeah, I understand. Yeah, I think I have another question from Hans. Hans, do you want to ask the question yourself? You can unmute yourself if you want to. Yeah.
Sure, it's not noisy here. No, I missed the first part of your presentation, unfortunately. I was wondering, I saw you showing some slides about ITER, tokamak reactors. I was wondering, do you think it would be possible to develop a standard reactor design, almost as an open source type of design, which could be copied all over the world within this program, within, say, like 20 years from now?
I'll tell you this. I foresee that in a development like this, you would go like you build a few and you learn from that before you order 10 or 100, right? I mean, just think of the investor. Would you buy 100 power plants when you have seen none that work?
No, I wouldn't.
No. Yeah, and then there's the construction time. So it takes about 10 years to put these things together, get them licensed, start them up. Mm-hmm. And that might, so what I'm very worried about is the innovation cycle, because I don't think the first one that has been designed will be the best. So if you want to allow yourself to learn and to bring in new technologies, so maybe the first one has conventional superconductors, and maybe the second generation has high temperature superconductors. So then it's a completely different design.
Yeah. If I may ask a follow-up question, and I'll stop. my concern is the ownership of the technology. If you look at conventional power plants, and different companies own different licensed technologies, I think that could hamper the wide-scale introduction of nuclear fusion quite significantly. So do you think that it would be possible for the world to say, be the owner of such technology?
Fusion has a track record of sharing everything, and almost nothing is protected. But and in a way, it's because we think these aspects are the least of our worries. So we would be in a good place if ownership is a problem. But you remind me a bit of. I once gave a lecture to a big room, well, actually the General Assembly room of the United Nations, filled with children, almost grown-up children of diplomats. And I asked them, what do you think is difficult if you want to build a fusion reactor? What kind of problems will you encounter? And so the hands went up, and I asked them what they thought, and they said, governance, sir. I was thinking of materials and stability, and stuff like that. But right they were. Governance is indeed the big issue.
Very nice question, Hans. I have another question from Tim Kaasjager. Do you want to answer the question? Ask a question, Tim?
Yeah, am I unmuted now?
Yeah.
Okay. Yeah, that was. I think it couples pretty well to the remark from just now. But I was just wondering when, because you speak of the historical evidence showing these curves with the technologies that we have up till now, and you compare trace similar trajectories for the future of nuclear fission and other things. But I was wondering, there are so many social, political, economic factors that, especially when considering the pressure from things like a Paris Accord or something, that couldn't they just completely shift the possible trajectories and be taken into consideration as well when making these assertions?
Yeah, clear enough. So this model assumes that there is no technical issue that you can build, that you don't stumble on technical issues, and then there's infinite market pool. It just asks how quickly can you build up the capacity to build all this stuff. There are zillions of reasons why it could go slower than that. So this is really the premise that you say, how fast could it go? And yeah, so if politicians don't come to an agreement or so, that might add decades. But my worry is that it's very difficult to go faster than these curves, or very expensive, if you want. And when I say expensive, it's not expensive on a small scale, but on a scale that is big by any standard.
Yeah, I think we have another question from Martijn. Martijn, do you want to ask the question yourself? You can unmute yourself if you want to.
Yes, Niek, thank you very much for your presentation. You actually mentioned that for the current energy transition and to meet the 2050 Paris goals, we should mainly look at technologies that already have proven themselves. I was wondering, what's your vision on normal nuclear reactors to contribute to reaching the 2050 targets?
Yeah, so I wasn't only speaking about technologies that have proven themselves, but that are big already. Because if you're already quite big, then growing from there to really significant is not so large a step anymore. So quite apart from all other considerations, so just if you just ask me technically what could fission contribute, you'd say, okay, well, there are about 430 plants at the moment, and the world capacity to build them is about between 5 and 10 per year. So that's just enough to or not even enough to keep that number where it is. So if you wanted to increase that to 10 times the present number, you would have to look at all the constraints, but definitely that would be a serious expansion in the industry. So it's that is not going to happen overnight. You would again have to build up that capacity. Having said that, of course, it is still in the same ballpark in numbers as wind and solar at the moment. So yeah, it could contribute.
Yeah. Okay. Thanks.
Yeah, we have another.
But it's also a very big effort that the world would have to make. It's not something that we can always pull out of the pocket if all else fails or so. It's even also nuclear would require a huge effort.
Yeah, I can imagine that's also a really complex technology to grow. It's probably easier to scale up wind turbines or solar than the capacity to build up nuclear fission.
Possibly, yeah. I mean, at some point, if you know how to build 100, you also know how to build 1,000, I would say, but you need to scale up.
I have a question from Henk de Vlucht. You want to ask the question yourself? You can unmute yourself.
Yes, I just did. I come back, Professor, to your conclusion that we need a kind of a toothbrush approach in order to match in 2050 zero emission or the Paris targets. And I was just wondering, does something like that exist, or is this purely a mathematical conclusion?
Well, I mean, to some extent, solar panels. So back in focus. To some extent, solar panels are becoming so cheap, the panels themselves, that they start to move into that range because people take new panels because they have higher efficiency and they're cheaper. I mean, I have panels. My roof is full of solar panels, and I've had them for 10 years, and they're absolutely not, not at the end of their life yet. Still, it starts to be a consideration, economical consideration, to have to have new ones that are, well, I don't know, a quarter of the price or less, and have higher efficiency. So the investment would be relatively small, and so that is a bit moving in that direction, that the economic payback time is short or shortening, and it starts. Yeah. Nobody asked the question how this solar panel industry can make a profit if it doesn't sell any electricity, as was my statement. Are you curious at all after that?
I think it's because people believe, at least enough people believe, that it could substantially help solve the problem and therefore are willing to invest into it. I mean, I bought solar panels myself 7 years ago, and I still haven't gained back the investment in saving electricity cost. And I did this because I believed in it, and I'm even considering what you say, and after 10 years to do them away by cheaper ones with a higher efficiency, because there is belief behind it. So yeah, probably that is it. Like in the stock market, the belief of the investors is a very important. The trust and the belief of the investors is a very important factor, and not just pure calculation.
Yeah, no, there's an emotional aspect to it.
Yeah.
Thank you. Thank you, everybody, for asking these very interesting questions and sticking around until the end of our 4th lunch lecture of the Physics Symposium. We would love to see you tonight for our evening lecture by Professor Robert Dijkgraaf and George van Hal. For more information about this, visit our website, symposium.vvtp.tudelft.nl. And thank you. And until tonight, you may leave the Zoom lecture now. Thank you.
Thank you all for participating. It was my pleasure.